So, so how Matt previously anticipated, we are now going to see the details of the TumbleBit, an untrusted Bitcoin-compatible anonymous payment hub. And we are having Ethan Heilman and Leen AlShenibr to present.
Hi, so I'm going to be talking about TumbleBit, which is our untrusted private Bitcoin payment system. So TumbleBit provides payments which are private, so they're unlinkable when used as a payment hub, or provide set anonymity when used as a classic Tumbler. They're untrusted, so no one, including the Tumbler, can steal your Bitcoins or violate your privacy. And when used as a payment hub, it's scalable. Furthermore, it's compatible. It works with today's Bitcoin. There's no malleability concerns. And this is somewhat tricky because we're going to have to rely on the very constrained opcodes that currently exist in Bitcoin to do some of this cryptography. So there's two ways to use TumbleBit. The first way is to use it as a classic Bitcoin Tumbler that provides k-anonymity. This is, you can almost think of this as a more private version of CoinSwap. So it has 4 transactions that are confirmed in 2 blocks, so it has a minimum mixing time of 20 minutes. And then we can use TumbleBit as a payment hub. So this provides unlinkability within a payment phase, but payments are confirmed within seconds because they're off blockchain and they don't take up space because we're going to be using unidirectional payment channels. So before I explain how TumbleBit works, I'm going to do a brief reminder of a unidirectional payment hub, and then I'm going to evolve that into TumbleBit. So Alice and the payment hub have a unidirectional payment channel. The payment hub and Bob have a unidirectional payment channel. This is implemented with 2 escrow transactions, which are 2 of 2 multisig. So they require both parties on each end of the escrow to sign off to spend that escrow. So Alice wants to pay Bob through the payment hub. So she does a claim transaction. The payment hub creates a claim transaction as well. And to authorize this payment, Alice signs that claim transaction. The payment hub signs the second claim transaction. And then when they want to close the channel, the payment hub can sign claim 1, Bob can sign claim 2, and the payment goes through. So the payment hub gets 1 Bitcoin and also sends 1 Bitcoin on to Bob. But there's a problem with this. The payment hub could be malicious and just take Alice's Bitcoin and never sign the second claim transaction and walk away with the money. So one of the traditional strategies is to make claim 1 and claim 2 atomic. So they either both happen or they don't happen at all. You can see that this would actually fix the problem because it's this lack of atomicity that allows the payment hub to solve. So one of the ways this is done is with hash locks. You have h of x, so you have some value x, and the claim transaction can't happen without x. So even if the payment hub signs it, Bob can't take the money until Bob learns x. So Alice creates a second hash lock that uses the same x, and when the payment hub claims the funds, it has to release that value x. Alice can tell Bob what this x value is, and then Bob can take the funds. So using these hash lock transactions, or HTLCs, the payment hub can prevent theft. The problem, though, is that if you have a bunch of people using this, the payment hub can link the hash locks that are used. It can see that Alice 1 is paying Bob 2 because they both are using the same hash value, hash input preimage. So it provides no privacy from the payment hub. So the main idea behind TumbleBit is to provide this atomicity, but in a way that's unlinkable. So the payment hub can't see which transactions are atomic, but they'll still be atomic. You can kind of think of it like unlinkable or private HTLCs. So the main cryptography I'm going to use to do this is RSA. And we introduced the idea of RSA puzzles. And an RSA puzzle is just a textbook RSA encryption of some value epsilon. So and it's always going to be the Tumbler that's creating these RSA puzzles. So the Tumbler has a public key, and it performs the RSA operation on epsilon and generates Z, which is our RSA puzzle. Now, notice that the Tumbler has secret key. And because the Tumbler is doing textbook RSA encryption under its public key, only the Tumbler can solve these puzzles. So if the Tumbler is given a puzzle Z, it can use its secret key to invert the operation and get epsilon back. So the Tumbler can issue these puzzles and the Tumbler can solve these puzzles. But the nice thing about this is that we can use RSA blinding to blind the puzzles. So we have a Tumbler. The Tumbler gives out two puzzles, Z1 and Z2, to two different Bobs. Bob 2 blinds his puzzle to Z star and sends Z star to the Tumbler. And the Tumbler can now solve this and end up with a blinded solution, which is epsilon star, and send it back to Bob. And Bob can now unblind this epsilon star to the original solution to Z2. And if Bob does this over Tor, so the Tumbler doesn't realize the Tumbler's talking to Bob, the Tumbler can't link which puzzle it solved. It knows it solved a puzzle, but it doesn't know whether it was Z1 or Z2 because the puzzle that was sent to the Tumbler was blinded. So TumbleBit has this, is sort of based around this idea. So what the Tumbler is going to do is the Tumbler is going to say to Bob, I will, if you solve this RSA puzzle, I'll give you 1 Bitcoin. So, and the Tumbler says to Alice, I'll sell solutions to RSA puzzles. So you can see how this might allow Alice to pay Bob. Bob gets a puzzle, asks Alice to solve it. Alice pays 1 Bitcoin to solve it, sends the solution to Bob, and Bob then redeems 1 Bitcoin. So on the right side here, Bob's going to do a protocol where if he learns this solution epsilon, he'll get 1 Bitcoin. And on the left side, we're going to do a fair exchange of 1 Bitcoin for a solution to a blinded puzzle. So first I'll explain how Bob does this, and then I'll fill in the fair exchange here once we've completed the Bob side of the protocol. So the Tumbler is going to create an RSA puzzle with the solution epsilon, and then it's going to take a signature, an ECDSA signature, and encrypt it under the solution to the RSA puzzle and create this ciphertext C. Now, this signature is actually going to be the signature to a transaction that allows Bob to spend 1 Bitcoin out of this escrow. So notice that if Bob learns epsilon, he can decrypt C to get sigma. And so if Bob solves this RSA puzzle, he can learn a signature, and he can use the signature to claim 1 Bitcoin. So the Tumbler sends the puzzle and the ciphertext to Bob. Bob blinds it, sends the blinded puzzle to Alice. Alice performs a protocol here and gets the blinded solution. Bob can now unblind this puzzle, decrypt the ciphertext to get the signature, and now Bob has a valid signature on this transaction and can get the coins from there. I'm going to talk about the fair exchange from Alice to Tumbler, but I want to note that you could actually use zero-knowledge contingent payment here. Basically what's happening is that Alice wants to trade a solution to some puzzle for a Bitcoin. We don't actually use zero-knowledge contingent payment. We've created a very performant protocol because this is 2048 RSA and would be fairly slow in ZK snarks. But this part could clearly be solved by a ZKCP. So Alice sends the blinded puzzle to the Tumbler. Similar to the Tumbler's earlier actions, the Tumbler is going to solve the blinded puzzle and get epsilon star. But notice if the Tumbler just told Alice epsilon star, then she'd be able to get money without paying for it. So the Tumbler is going to encrypt the solution using this key X, and is going to hash X to this value Y, and then send the ciphertext and Y to Alice. So if Alice learns X, Alice can decrypt Q and get epsilon star. And then Alice is going to create a transaction which offers 1 Bitcoin from this escrow if the Tumbler reveals this value X. And if the Tumbler takes that 1 Bitcoin by revealing the value X, Alice can now decrypt Q and get epsilon star and then send that back to Bob. The problem here, though, is that the Tumbler could could not play fair. The Tumbler could generate C here that's just some random value, and then when Bob goes to decrypt it, Bob wouldn't get a valid signature. And also the Tumbler could play games here too with just do crap. So the way that we solve this is we have two protocols. One is called the Puzzle Promise Protocol, and this protocol allows the Tumbler to convince Bob that the solution to the RSA puzzle is a value E, which allows him to learn a valid signature on his transaction. And the other protocol is the Puzzle Solver Protocol, where the Tumbler convinces Alice that the preimage X will allow her to learn epsilon star. Both these protocols are actually fairly similar. They use similar tricks. If I have time, by the end of the talk, I can go into the Puzzle Solver Protocol, but I might not have time for that. But I do have a slide, so if anyone wants to go more into the details, I'll be happy to show them this. So TumbleBit uses 3 phases. In the first phase, all the payment channels are set up. And each of the Bobs are given ciphertext and RSA puzzles. Now, we want to be able to make multiple payments. We don't want a payment channel that you can only use once. So there's actually additional ciphertext and RSA puzzles. Each one gives an additional Bitcoin to increase the payment channel. But we don't want Bob just to solve the last one and say get 10 Bitcoins. So each puzzle is actually locked until Bob finds the signature and then can use the signature to unlock the next RSA puzzle. The next stage is the payments phase. So this is where payments happen. We imagine this maybe about like 1 month or less than that. So let's say Alice wants to pay 1 Bitcoin. She pays 1 Bitcoin to the Tumbler using the fair exchange. And Bob receives a signature, which now allows him to increase that payment channel by 1 Bitcoin and also unlock the next puzzle. Alice pays again. Bob gets another signature, unlocks the next puzzle. Another Alice pays and unlocks another puzzle and gets another signature. And we can imagine lots of these payments happening. I've only drawn 4 signatures here, but there's a ... This actually goes to 10. And at the end of the payment phase, we have a cash out phase. Now, the cash out phase allows everyone to take their money out of these payment channels. So Alice 1 spent 5 Bitcoins, so the Tumbler gets 5, and the same for Alice 2 sends the Tumbler 3, and so on. Bob 1 got 2 signatures, so he can use the second signature to sign a transaction that gives him 2 Bitcoins. Bob 2 actually got 10 Bitcoins, so he can sign a transaction that gives him 10 Bitcoins, and so on. So the privacy offered by the TumbleBit payment hub. Well, let's look at what the Tumbler sees. The Tumbler sees each time an Alice paid. It knows the time, and it knows that Alice paid someone, but it doesn't know who Alice paid. At the end, the Tumbler learns the aggregate value that each Bob got, but not when those Bobs were paid or who paid in. So the Tumbler sees the payer of each payment, and it sees the number of payments each payee received. So our unlinkability definition is that all interaction graphs, so this Alice, say, spent 5 Bitcoins, and this Bob got 10 Bitcoins. We refer to an interaction graph as any way this could have happened between all the parties. So we're unlinkable in that all interaction graphs compatible with a Tumbler's view are equally likely. So this could happen, or this could happen, or this could happen. Now, I've only showed a few interaction graphs, but there could be an extremely large, any interaction graph which ends with this Bob getting 10 and this Alice sending 3. They're all equally likely. There's no way the Tumbler can figure out which set of interactions led to that. And Leen will now explain this part.
All right, so as Ethan mentioned, TumbleBit can also be used as a classic Tumbler, which allows users to move coins to an unlinked fresh address. Oh, sorry. All right, so as you can see, an old address goes through the Tumbler and then gets a fresh address, and you can't tell what the old address was. And to run TumbleBit as a classic Tumbler, you would basically open a payment channel with the value of 1 Bitcoin that can only be used for one payment. And in this case, we'd have an equal number of payers and payees, which offers us a K-set anonymity, where K is the number of payers and payees. So to solve the anonymity problem, a number of schemes have been proposed, schemes that propose new cryptocurrencies like Zcash or Monero, and schemes that are Bitcoin compatible, which are like mixers. So blind coin is vulnerable to Bitcoin theft, while CoinSwap can break anonymity. CoinJoin and CoinShuffle are vulnerable to DOS and Sybil attacks, and CoinShuffle has a limited anonymity set since it's limited by the transaction size, which is just 100 kilobytes. Zim is not vulnerable to any of these attacks, but takes a long time to run. And so we have implemented a proof of concept implementation of the classic Tumbler, and we're currently working on improving it, and we have the source code and the development roadmap available on GitHub. So our implementation is performant. It only consumes 326 kilobytes of bandwidth. Most of the time is spent on the puzzle solver protocol, and if you run TumbleBit on the same machine, like with the server and everything, it only takes 0.6 seconds. If we run the server in Tokyo and like both Alice and Bob in Boston, it would take 6 seconds, and if you run them through Tor, it would take 11 seconds. And yeah.
So, in conclusion, TumbleBit provides private, untrusted, scalable payments on today's Bitcoin. We have running code for the TumbleBit Classic Tumbler. Our code runs on, we've run our code on Bitcoin's mainnet blockchain, so you can go and look at our tumbles. We've published our code on GitHub, so you can read it. But we're working to improve the code and make it easy and safe to use. Currently, it's a proof of concept. It works. You can run it. But we want to make it far more secure. We wanted to prove that we could do it, but making it safer for users is going to be what we're going to be working on now. And we are trying to hire a full-time engineer. So email me if you're interested. And I believe I have enough time to explain one of the protocols, so I'll come back to questions. So the puzzle solver protocol, remember this is the one that allows Alice to exchange a blinded solution for a blinded puzzle for a blinded solution. So we want it to be fair exchange. So we want Alice to pay the Tumbler if and only if the Tumbler provides a valid solution, and the Tumbler reveals the solution if and only if Alice pays. So we don't want either party to be able to cheat each other. So Alice gets this Z star from Bob. And what she does is she's going to create M, what we call real puzzles, and N fake puzzles. Now the real puzzles are actually all blinded versions of Z star. So Z star is going to be double blinded. And so she just takes Z star and blinds it again and makes M of these. And the fake puzzles are going to be values that Alice chooses and that she then encrypts under the Tumbler's public key. So she actually knows the answer to these. And she's going to shuffle them together and send them to the Tumbler. And the Tumbler can't tell which ones are real and which ones are fake. It doesn't know which ones are going to be the fake ones and which ones are the actual answer that Alice wants. So the Tumbler is going to solve all of these. It's going to provide the solution to every single one of these puzzles that Alice has sent. It can't send the solutions back because then Alice would be able to take the money. So what the Tumbler is going to do is it's going to encrypt each one of the solutions under a different X, and it's going to hash all of these X's to get a hash output Y, a different hash output, and send these to Alice. And so it's in this stage, the Tumbler is essentially like committing to these solutions without revealing them. Alice is going to then reveal which one of them are fake. So she says to the tumbler, if you tell me the solutions to these, I don't learn anything new because I actually already know the answers. So here are all the answers to the fake puzzles. The tumbler checks that these are in fact real answers to the fake puzzles, and it's going to reveal the keys that allows Alice to decrypt these fake puzzles. And so Alice can check that all the fakes were actually computed correctly, that the keys actually hash to Y, and that when you decrypt it, you actually get a valid answer. So Alice proves all the real puzzles unblind to the same puzzle. So she actually gives all the blinding factors over so that the tumbler can see that she'll only be getting one answer. And at this point, they're good. Alice provides a transaction that actually asks for all the X's to the reals. The tumbler provides all the X's to the reals. And so the tumbler gets paid 1 Bitcoin. Alice gets paid, Alice learns all the X's, which he can use to decrypt all the Q's and learn epsilon star. Now notice that if the tumbler computed any of the reals correctly, Alice will learn epsilon star because all the real puzzles are actually all to the same Z star. And that if the tumbler tries to cheat Alice, the tumbler must corrupt all of the real puzzles. It can't just corrupt some of them. And if the tumbler corrupts any of the fake puzzles, Alice will see that a fake puzzle has been corrupted. So the tumbler has to guess exactly which puzzles are the real puzzles and only those puzzles and corrupt them. So the probability that the tumbler cheats successfully is the number of real puzzles plus the number of fake puzzles choose the number of real puzzles. And so for our values, 15 and 285, this is 1 over 2 to the 80. And we chose this number because this is the collision resistance of RIPE-N 160. And so this is a very small number. Let's see. So I can answer any questions.
So 2 questions. We are running a little late.
How do you attract liquidity? Is your plan to build this into a central part of the protocol, or are you going to have other hubs that people have a reason to add their coins to? And if so, how do you incentivize them? Are you going to pay them for adding their coins?
So I think this is a question about incentives and setting up the system. So I didn't talk about it whenever I showed it. It was always like 1 Bitcoin for 1 Bitcoin. But it's very easy to build a fee into it. You probably would only want like 1 or 2 of these because the more people that use it, the better the anonymity provided.
Yeah, Brian Ford from EPFL. Very cool, interesting work. I like the kind of the clever use of Chami and eCash for this purpose. So one issue, though, I don't quite understand how or why, on what basis you're asserting that this approach is less vulnerable to Sybil attacks than others like CoinJoin and CoinShuffle. In that it seems like the Tumbler, maybe there's 1,000 Alices and 1,000 Bobs, but 999 of the Alices and 999 of the Bobs might be fake Alices and Bobs that the Tumbler created, right? So how do you, how is this any better than in the CoinShuffle or CoinJoin world?
In terms of comparing it to CoinShuffle or CoinJoin, one of the advantages that a Sybil attacker has is that a Sybil attacker can abort. And so if the Sybil attacker doesn't win in any particular round, it can start that round over again. CoinShuffle does have some protections against this.
Yeah, that's precisely the problem that CoinJoin has, but CoinShuffle does not, so that CoinShuffle solves.
So CoinShuffle solves it in the sense that someone can't abort again, but they get at least 1 abort, right? So if you have multiple Sybils, they just didn't get all the Sybils, they can do the abort. The other issue, and I didn't actually talk about this, is that we have these anonymous fee vouchers. So in the classic Tumbler mode, we use that to place a cost on the Sybils. So if a Sybil fails to de-anonymize a particular round, it just fails and that round happens. It can't re-abort. And each time it wants to try, it has to pay money, so it can't just leave and not pay any money. Within the payment hub scheme, we required that people lock some bitcoins in escrow in these payment channels, and that these payment channels, like a coin swap, all sort of add on top of each other. So if you just want to add, say, 30 Sybils, and there's 100 people that want to play, you don't get to replace any of those 100 people. You just add 30 additional Sybils, so that doesn't degrade the protocol. That doesn't degrade the anonymity set offered.